so that it's recording. Okay, yeah. So good morning, everybody. Thanks for joining today's extra class or compensatory class. I know Saturday morning 9:30 is not really a good time, but I expect the same kind of enthusiasm as you show usually in the class. So with that, so as usual, we will start by recapping what we did last class. So what we were looking at was in the last interaction was to model or understand a interface. Say for example, we took a nice well-behaved interface which is drop-in mercury electrode in potassium chloride, and this we approximated to something like a RS, and we had a CD component and an RF component, just so that we RF resistor component. So this is the equivalent circuit that we arrived at for this interface, and said that once, because the same interface, the reason why we have the RF here is because the same interface is going to go from is will transform, which will start as an ideally polarized interface and go over to ideally non-polarized interface. So this is for a small voltage window, and this, when the voltage window, the voltage applied exceeds the ideally polarized limit. Okay, limit. So this is the, and then we said that that is why we put the RF and the CD in parallel, and when RF is equal to 0, then you have all the current which will flow through the RF, so it will become an ideally non-polarized electrode, and RF tending towards infinity will make it an ideally polarized electrode interface. So this is the argument that we gave, and then we looked at the entire cell. This is just one half of the cell, so we looked at the entire cell, and then we were able to write down a final circuit for the entire cell, which is called the RC circuit. That is because you essentially have a, a battery, and you have an ammeter, and then you have a resistor RS, and the capacitor, which is going to give you a component CD connected in series. And so this becomes the entire circuit, RC circuit. So any operation, the idea of this is that this is what we call as an equivalent circuit representation. representation representation and any operation that we do on any perturbation or any measurement that any operation that we do on this circuit is going to have the same effect on this we can use these mathematical or the circuit components, say for example the ammeter, the DC power supply. These are all essentially the input parameters or the measurement parameters, and RS and CD are the system parameters. So now um, any perturbation that we do, and try to understand the influence of our perturbation on the RS and the CD, you will have you can do it in a circuit. You can use in a circuit analysis component. You can use in a circuit analysis route, and the same operation or the effect of the what we get through a circuit analysis method is going to be the same effect as what you would get in the physical picture, that is when a DME is sitting inside a KCl solution. So the idea is that you do a circuit analysis, understand the math of it, and then go back to the actual physical picture and try to correlate what is happening in the physical picture. This is an important component, and this bridge between the math and the physical picture, or the circuit, the abstract circuit and the physical reality, is what is called the equivalent circuit representation. Is this clear? And so then we went on and said that, okay, now if we apply a perturbation, and the perturbation is in the form of a, so the case 1 that we studied is a perturbation that is in the form of a potential step. Potential step. So when we apply that, what it means is that you start from some zero potential at time t equal to 0. You ramp up the potential almost immediately, instantaneously, and hold the potential constant with respect to time. Hold the potential. So this is the potential with respect to time. So it's held constant. Now when you do this operation on this circuit, on the RC circuit, this is being done on the RC circuit, and therefore the RC circuit represents the drop-in mercury interface, drop-in mercury electrode interface. And so the same operation is now being done on the drop-in mercury electrode interface. And so now when we understand how the potential step is going to change, or how it is going to affect the, how is it going to deliver, or the kinetics of the circuit responding to this potential step. And that is what we did through a calculus method. So we said that q equal, and the final result we got is either q equal to vcd into 1 minus exponential minus ts t by rs cd, or the current in the circuit is going to be raised as v by rs exponential minus t by rs cd. So so far clear, everything is fine. I'm just trying to, right? What happened?
Yes, clear.
Clear. Okay. So what so what we did was, so now then we looked at one such circuit. Say for example, this is the circuit. I'm redrawing the circuit here. So you have the CD and you have the RS. So this is the circuit RS CD. Now, if you apply a potential step, you will see that the voltage, we like let's see the charge. So this, I'm giving a voltage at the source mean VC VS, that is, and the voltage across the capacitor is going to be represented by VC. So now it is obvious that VC VC tends towards Vs. Vc can never be equal to Vs. Vc can never be equal to Vs. We say that Vc approaches Vs. That is, the potential of the capacitor can assume a maximum value of the potential applied at the source from the DC battery, from the DC source. It cannot exceed. There is no way that it can exceed the potential of the source. Okay, if you apply 5 volts, you can do only work that is the energy equivalent of 5 volts is what you will get. You can maximum get at the capacitor if you assume 100% charging. Okay, but the and you can't apply 5 volts and try to expect to get more than 5 volts. That doesn't that breaks the fundamental law of conservation of energy itself. That you are doing less work and getting more, spending less energy and getting more work. So that is absolutely not possible. Now, the reason why Vc can never be equal to Vs is also to do with the exponential nature of the curve. That means when you follow the capacitor voltage as a function of time, you will see that it starts to increase exponentially and then it starts to saturate. So this saturation behavior is the reason why we cannot, for with 100% we cannot point out and say that Vc can be equal to Vs, because an exponential function never gets to its limit. It always approaches its limit, and in this case the limit of this exponential function is nothing but Vs. So Vc can always approach Vs. Am I making myself very clear in this? the potential developed across the capacitor approaches the potential that is applied across the capacitor. It is not equal to zero. Even at infinite time of charging, you will still see a minuscule, infinitesimally small difference between the potential applied to the source and the potential applied to the potential generated across the capacitor. And that is very well understood because you have other circuit elements, mostly in the form of resistor, which is going to take some part of the potential, or capture some part of the potential. Okay, so that is why you don't see this going. Now in this curve, or if you see the same curve, if I were to draw it in terms of a current, then what would happen is that now the current is what we are trying to capture. So it will and you can see very well from the analysis that we did last class, from the maths of the math that we did last class, we see that the current is going to be V by Rs exponential minus T by Rs CD. So what it means is that the maximum value that this can take is I equal to V by Rs, and that's exactly beautifully boils down to Ohm's law, V equal to IR. Okay, so the maximum value that the current can take starting from zero current is given by V by Rs, V over Rs. And now after that, after it reaches the maximum value, what is going to happen? The exponential function is going to take over, and that would lead to a decrease in the current, the exponential decay in the current. And this nature of this decay, the magnitude of this decay, is controlled by T by Rs CD. T by Rs CD. And also we saw that this T now starts to become more and more prominent, or more and more relevant, because the time at which the property of the capacitor, whether it is the voltage or the current or the charge, any of these properties, a charge stored in the capacitor, any of these properties in the capacitor is going to be controlled by this time constant T, and the Rs, the resistor component Rs, and this capacitor component, capacitor itself being a component CD. So this time when we say okay, maybe I should why is this when I try to do this, I can't put a new slide when I'm in the PowerPoint mode. Okay, so now there is a problem here. Excellent. My computer is acting up. So what we are saying is that for a potential, I'm just trying to summarize this. Okay, potential step. Please bear with me if I'm repeating myself too many times. The potential as a function of time is going to increase exponentially, reach into a limiting case of Vs. This is the potential across the capacitor. Okay, the limiting value of the potential across the capacitor is going to be the potential across the source. Now, and the other parameter that we can monitor is the current across the capacitor. I'm just drawing it in the same time scale. So the current across the capacitor is going to increase, get to its maximum value of V by Rs. This is the maximum value the current can take, and then followed by an exponential decrease. The nature of this exponential decrease is going to be dictated by T by Rs into CD. And then finally, the charge stored in the capacitor. I'm plotting everything versus a common T. The charge stored in the capacitor is also going to increase as exactly like what potential would do, and reach a maximum, tend towards a maximum value. And this charge, let me put the maximum value as Q, capital Q. So this Q is always going to tend towards. So what we see is Vc is going to tend towards Vs at uh, T as T tends to infinity. The current in the capacitor tends to zero as time tends to infinity, and then the Q, the charge in the that is developed in the capacitor, tends to some finite value Q as T tends to infinity. These are the three the three curves which help you understand and appreciate the response of the interface, response of the capacitor that is developed at the interface because of a potential step, by the application of a potential step. So now if you one more Uh, One more important aspect when we talk in the that we need to discuss also is that there is, like I said, everything is going to be time dependent function. Okay, it's either an exponential increase or exponential decrease, both of which are time dependent functions. Now, what do we? How do we? Um, um, uh, so in reality, when it comes to practice, we cannot wait for infinite time for and say that the capacitor is reached the maximum state. Okay, we cannot do that. That's not a very tenable approach, in a practical approach in a real time. So what we do is we take by convention, we say that, see, this T by RSCD, we have already seen that this RSCD component is what we call as the time constant of the circuit. Time constant of the circuit, of the circuit. RS into CD has the dimensions of time. I forgot to give you the assignment. I'll do that uh, immediately after the end of this class. Okay, sorry about that. So what you need to establish or convince yourself is that this component RS into CD has the same units of time, and this is called the what we call as the time constant of the RC circuit, of the, to be more precise, time constant of the RC circuit. Okay, so this time constant, because in real time we cannot wait for infinite time for the either the voltage or the charge to saturate or for the current to drop to zero. Waiting for infinite time in real time doesn't make sense. So what we say by convention is that this time constant, T, or in some books you would have, most of the books use the symbol tau for representing the time constant, which is nothing but RS into CD. So now 5 times the time constant, or 5 times tau, is what is called, when you look at a time scale beyond 5 times. So when the time you are looking at is larger than 5 times the time constant of the circuit, then you are in steady state. That means don't any further change in the voltage, current, or charge stored in the capacitor is not happening, is infinitesimally small, and therefore it can be neglected. For any time less, any time that you are interested in, which is less than 5 times t or 5 times tau, you are looking at a transient state where the potential, current, and the charge across the capacitor is going to be a time dependent function. Okay, so it will have a time evolution when you are looking at. So let me, in this graph, because I have the way I wanted to write this, if I say this is my 5 times the time constant, so this entire part is a transient part, and from here to here, okay, where you will see a dynamic evolution of charge, current, or voltage across the capacitor. And after that, after 5 times time constant, you see a steady state part, where you can for safely assume that the capacitor has reached its maximum voltage, the charge stored in the capacitor is 100%, and the current flowing through the capacitor is 0. Okay, so that is the important difference here, where you see that 5 times, this is purely out of convention. There is no particular tomorrow, if and every one of us agree that 5t is not the steady state, 10t becomes the steady state, then so be it. Okay, but for the time being, conventionally we have decided, everyone has taken a common ground and decided that 5 times time constant is what determines the boundary between transient and the steady state part of the capacitor. So the transient part being that the domain where you will see a continuous evolution of potential, current, or charge stored in the capacitor, and the steady state part being that either the potential, current, or the charge is set to not change with respect to time. Okay, and all this is for a potential step that is given as an input. Is this clear so far? Any questions so far?
Subbu, I have one question.
Yes, please.
Um, So when you, the double layer capacitance, I want to get some intuition here. So the double layer capacitance is of the order of something like microfarad.
Yes, microfarads per centimeter square.
So yeah, so if even if I assume something like 20 centimeter square, it's still microfarad order,
Yes,
and
yes.
if the resistance is of the order of say 1 or 2 ohm,
Yeah.
so the time constant is something like some microseconds, is it?
Yes, milliseconds or microseconds. That's exactly what we are going to look at.
Okay, so we do have devices which can measure this potential change over
Oh,
milli.
absolutely, absolutely. Every single device, remove, when we will do this, you will be surprised that every single device, almost every single device, including your phone, works in the millisecond or microsecond time scale. You see, when you look at a processor, okay, so when you want to buy a say computer, you start looking at Intel i5, something i5. Now i10 is come to the market. i9 or i10 is the latest model that has come to the market. Intel i9 or i10, I'm not sure. And this gives you a particular frequency. It says say 120 hertz, or this one maybe be 600 hertz, right? This is what is called the clock speed. You want a higher clock speed. So when I say 600 hertz, then in terms of time, this is 1 over 600 seconds, and we are talking about millisecond time scale. So every single component, that most of the components, either you knowingly or unknowingly that we interact with, work in the millisecond time scale.
Right. Okay. Thank
Millisecond or even microsecond time scale. The smaller the higher the frequency, smaller is the time, and the smaller is the clock speed, and therefore faster is the processing speed. That is the implication. But this I don't want you to directly relate the 600 hertz to the capacitor. That is not the idea. But I'm telling this only to give you an idea that milliseconds and microseconds are extremely routine functions, or extremely routine realistic timescales that we encounter in practice.
So fortunately for us, it's in millisecond or microsecond. So if I take a very low capacitance, which is like nanofarad, then
Uh,
I'm in trouble.
then you will have nanosecond time scale of response is going to be of the order of nanoseconds, because your resistor is going to be still finite, like some
Yeah.
bigger value. Yeah.
Yeah. So measuring that would be that much harder. So I'd have more advanced electronic.
Measuring the see, when you get into nano, or nano is still fine. Nano ampere current is very much possible. Okay. When be below nano, when you go to picoampere or femtoamperes, then you have to have a lot of you have to exercise a lot of caution, mainly because your your electrostatic noise starts to interfere with that kind of current. Okay, because everything is made up of interfaces, and any interface can build up some kind of electrostatic interference. Okay, when I say electrostatic interference, you have, see, even when you're actually soldering, okay, you put this solder and connect two copper wires together. You think that everything is fine, but no, because you have a copper, two copper wires and a solder in between, or solder somewhere creating an interface, and that work function of the solder and work function of the copper are different. So if you want to be extremely precise, you can actually measure a potential between the copper metal and the solder. That potential is because of the work function difference between copper and solder. Okay, so in that sense, then once you have a potential, then you will have a junction current. Okay, so that when you go below nanoamperes, these start to become increasingly important. So for example, if you want to measure really small currents, you don't use the lead tin solder that we use. You use a special kind of solder which is made up of indium. Okay, and your circuit elements are going to be extremely different, because you will have so much of electromagnetic radiation floating in the atmosphere. Your mobile phone here gives you electromagnetic radiation. the laptop wirelessly working wirelessly gives you electromagnetic radiation. So you want to shield. So when you want to measure pico or femtoampere of current or femtoampere of voltage or femtoampere of charge, femto voltage or very extremely low femtocoulombs of charge, then what you will have to do is you have to shield even the current carrying lines which do the measurement for you, which connects which basically connects the different components and does the measurement for you. Even those has to be shielded from the external electromagnetic source. Though that is done by what is called as coaxial and triaxial cables. Coaxial and triaxial cables. So this so to answer your question, till nanoampere we are fairly okay, but the minute we go below nanoampere to femto or pico amperes, or femto or pico of any current unit, any current parameter, then we will have to take a huge amount of precautions.
Got it. Thank you.
Yeah. Okay. So now, wait, where did that? Okay. So that is what maybe I should. Oh, yeah, it's fine. Um, keep. Why am my laptop is behaving crazy? Okay. So now this is what we can actually go ahead and see is see the what is called as a RC charging table. Remember, this is only for a potential step, an RC charging table in where we can look at various time constants of the circuit, say 0.5 time constant, 0.7, 1, 2, 3, 4, and 5 time constants, and the RC value for that, and then what is going to be the percentage of voltage of the capacitor when compared percentage of the maximum. Okay, so the maximum for the capacitor for in terms of voltage is the voltage of the source. So what percentage of the voltage of the source is there at 0.5 time constant, you will see that if you do the math you will get it to be 39.3% of Vs. Then 0.7 is going to give you 50.3% of Vs. Similarly, if you move to 5 time constants, you see that it is 99.3% of Vs. Okay, so this is where I said that it is not exactly equal to 90%, equal to 100%, but we can't wait endlessly. Okay, so the increase beyond this 5 time constants is going to be very small. So even if you go from 5 to say 100 time constants, you will only see that 99.3 goes to 99 point say maybe 4. So the increase or the change in the voltage stored across the capacitor is going to be minuscular after 5 times time constant, and therefore we say that capacitor reaches 100% charge state or 100% Vmax within 5t. This is purely a conventional assumption that we make. Similarly, for the case of current, if you see current is going to be the maximum is going to be V by Rs, and after that it is going to decrease. That is what we have seen here, V by Rs. So V by Rs at immediately after 0.5 at time t equal to the moment you apply the potential step, it is going to go to V by Rs, and from that point onwards it will start a decay. It will start to decay. So then it is going to be starting from 60.7. By the time you reach 0.5 time constant, the current is already 60.7% of V by Rs, and now 0.7 time constant, 49 roughly 50% of V by Rs, and by the time you come to 5 times time constant or 5t, you see that it is only about 0.7% of V by Rs, which means that current also tends to zero, and practically beyond any particular beyond 5 times time constant, the current in the circuit can be taken to be zero. Okay, and that is why this 5 times time constant is purely a conventionally fixed parameter. Just like we say that electrons are negatively charged and protons are positively charged, neutrons are doesn't carry any charge. It's purely a matter of convention. Tomorrow, if we decide to call protons as negatively charged particles, so be it. If the International Union of whatever decides, okay, from tomorrow onwards protons are negatively charged, absolutely nothing of the science and our understanding is going to change. Absolutely nothing. Okay. Remember, the whole idea of negative and positive charges itself is relative. Okay, so there is nothing that is going to absolutely nothing that is going to change in our understanding if we call, say, protons as negatively charged, or if we decide to move the 5 times time constant to 10 times time constant. Okay, is this clear so far?
Yes.
Okay, so then we will look at, so this is the discussion centering around the potential step. Now there is also a different kind of, like when we talked about the measurement in general, I said for an electrochemical or an electrical measurement, the main two parameters that we decide that we can control and observe is, you either control the potential and observe the current response in the system, or you control the current and observe the potential response in the system. So the first case was case 1 that we looked at for the potential step, is where we controlled the potential applied on the system and looked at the current response of the system. So now we can do the other way around. We apply a current step to the system. So that means current starts from I equal to 0 at t equal to 0, and then it is stepped up to some finite value, and then after which the current is held constant with respect to time. Again, if you do the same kind of math, you will see that, and the circuit is exactly the same. The circuit is basically a DC power supply, and then a meter, and then you have a CD component and an RS component. So this is exactly RS into CD. So the the circuit is exactly the same, meaning that you are looking at the same drop in mercury electrode in sitting in potassium chloride solution, except that instead of applying a constant potential, you are applying a constant current. Now what happens is that you can write down the Kirchhoff's law, V equal to, so again the voltage is going to depend on the voltage, the total voltage applied is going to be broken down into VR plus VC. There is no change in that, except that VR is now again given by I into RS, but VC, the current across the capacitor, because you are applying a constant current, the potential across the capacitor is now going to be I by CD into integral of dt, or from 0 to t. So because you are applying a constant current in the system, and so now if you look at this and try to arrive at the math, you will see that V is equal to IRS plus, this is a fairly very simple integration compared to what we did last time. So this is RS, I into RS plus T by CD. This is the expression that comes out for the voltage. Remember, when we apply current as an input, we look at the voltage as the output. So now if you plot the output, so this is the input that is given into the system, that is the perturbation done to the system. The output, which is what we study as a response of the system in terms of its potential with respect to time, is now given by this V equal to IRS plus T by CD. This means that it is a very straightforward graph. You see that it's a positive slope. The slope of that is going to give you I by T, I over CD, and the y-intercept of that is going to give you IRS. This is of the form y equal to mx plus c, and c is this component, and mx is the mx is this component. Okay, so your basically your output is going to be increasing potential, the potential which is increasing, constantly increasing with time, as long as you are applying the current, stable current. As long as you're applying a stable current, that means the potential across, which is generated across the capacitor. Remember, this is potential generated across the capacitor. Okay, the potential generated across the capacitor is going to keep on increasing. This means that so that's what I have written here in words, for a current step. If you doing a current step, the potential increases linearly with respect to time. This is one of the current step has a very interesting limitation. As with the case with the potential step, you can keep on applying the same potential. Okay, it doesn't matter. The current is, after a certain time, the current drops to zero. The potential across the capacitor reaches a maximum value, and there is no problem with that. But the problem with the current step is, or one of the aspects of applying a current step sorry, excuse me. So one of the aspects of applying a current step is that if you keep on applying a constant current to the system, you see that the potential generated across the capacitor keeps on increasing. This is a problem because you don't want the potential across the capacitor to keep on increasing. Reality connected to the reality, the picture that is happening in real time. You say that the potential across the DME from and the KCL interface is increasing with respect to time. So this, if you do it continuously, there will come a time where the ideally polarized interface is going to transform over to an ideally non-polarized interface. That means the charge transfer between the drop-in mercury electrode and KCL is going to happen, and that is a state where which we refer to as catastrophic failure. Catastrophic failure. You don't want to go into that because you are now breaking the electrode, you are breaking the interface, you are breaking the double layer, or you are breaking the property of the interface to behave as an ideally polarized interface or ideally polarized electrode. Okay, so the current step always has a risk that at some point of time, if you keep on applying the current, your potential generated keeps on increasing without any limiting value, and then once it reaches the potential across the capacitor crosses over the ideally polarized potential for that particular interface, then you will start to see charge transfer happening. That means the ideal polarizability behavior of the electrode is broken down, is fails, and that is what we call as catastrophic failure. So in other words, the dielectric breaks down. The dielectric starts to break down because you are transferring charges from the electrode to the electrolyte. The electrolyte in this case is the dielectric. So the dielectric starts to break down. It starts to change chemically, and therefore the capacitor is no longer the dominant player in that picture. The capacitance is going to completely well, in a perfect sense, completely vanish. In real time, doesn't perfectly vanish, completely vanish, but in an ideal world, it's going to completely vanish, and that is what is going to be be referred to as a catastrophic failure of the capacitor. Okay, is this clear?
Yes.
Any questions so far? Any questions? Okay, so if that is the case, so then I'm just summarizing the, yeah, please, yes, you wanted to ask
Can
something?
we know? Can we know at what time this failure will occur?
Yeah, of course, because you know, for a given ideally polarized electrode interface, you know exactly what is the potential up to which it behaves as an ideally polarized interface. In case of drop-in mercury electrode and KCL, you know that mercury starts to oxidize at 2.1 volts. So when the potential across the interface crosses that 2.1 volts, you know that mercury will start to oxidize, so it will no longer remain as pure metallic mercury. Similarly, KCl is going to start reducing at some potential. So this potential is exactly known to us.
Okay, sir.
Okay. So I have just summarized the implications of the equivalent circuit representation in the two cases that we have discussed. One is the potential step and other is the current step. This is just a summary slide to tell you that this is the input to the system. In case of potential step, this is the output to the system, which depends on time constant the RS into CD. The nature of this exponential decay is going to depend on RS and CD, and we saw that in real time. And in case of current step, this is the input to the system, and the output to the system is going to be first, a linear increase in the potential across the system, and therefore you will have you will finally, if you continue doing the current step, you will finally end up with a catastrophic failure. So this is just a summary of what we looked so far. Now that there is a third interesting case, which will be that you are as opposed to the potential step, the third case is a potential sweep. So you are not applying a constant, the circuit element is exactly the same. Look at it, the RS in the CD, the battery VS, which is providing you the potential, and the current, the ammeter, which is measuring the current. So the circuit is exactly the same. But here, what we are doing is, you are starting from, say, VI, some initial value of potential. This VI can also be 0 or it can be non-zero. We are not bothered about that. So that means the potential sweep can happen after a potential step. So imagine that you're doing case 1 first. You're stepping up the potential. That has been maintained constant with respect to time. And after some finite time, you decide to apply a potential sweep to the circuit. That means you are increasing the potential with respect to time. The signal, that input signal that you are giving, is increasing with respect to time. And you know that the potential at any time t is going to be equal to the initial potential plus the rate of change of potential and time. So nu is the rate of change of potential with respect to time, rate of change of potential with respect to time. That is, in a mathematical sense, dV by dt, the rate of change of potential with respect to time. So then we can write that potential applied at any time t is going to be dependent on the initial potential that you take. If it is the initial potential is 0, this term simply drops off. It becomes equal to nu t, or dV by dt, in dV by dt into t. Okay, so it's fairly simple. So then again we go back to the same Kirchhoff's law, which says that the potential that is applied has to be split, has to be distributed between the resistor in the circuit and the capacitor in the circuit, except that this potential is now itself a time dependent function, which is given by Vi plus nu t is equal to Irs plus Q by Cd. And then you do the same kind of calculus that we have done for the, say, the case 1. I'm not doing going into the calculus, plus please, but request you to please work it out for yourself. No matter 100 times if I do it here, I can do the calculus here. I can do it 100 times. Doesn't matter. If you do it one time, it will get registered with you forever. That has been my experience. Okay, so please urge you to do the calculus for yourself. So it's a fairly simple integration that is involved. So the final form of that would be that current is going to be now equal to nu CD, because you have a new component coming here. The new is nothing but dV by dt, the rate of change of potential. Yes, so the new component comes in, so that it becomes equal to nu CD plus Vi by Rs minus nu CD exponential minus. So this term exponential minus T by Rs CD is consistently appearing in no matter what kind of input that you give, either in case of potential sweep or in case of, okay, potential step, it doesn't come because it's a linear function. But in case of a potential step or a potential sweep, you will see this exponential function coming out repeatedly. And that is why we have stressed on that and said that RSCD is what is determines, or what is called as the time constant of the circuit, and it determines certain very intrinsic physical property of the system. We will shortly see that. Okay, so here, but nevertheless, coming back to this argument of potential sweep, we see that now we can write our total current in terms of a component which is independent of time. Nu CD, it is independent of times. Nu itself is a rate of change of potential, so that is not dependent on time. The rate of change of, you are not accelerating the potential, you are applying a constant change in the potential. That change in the potential with respect for no matter what time interval you take is going to be constant. So this is a time independent part, and this whole thing, because you are sitting with an exponential minus t here, becomes a time dependent part. So that is why we call it as the first part is called as a steady state part. This is the steady state part, which is basically time independent, and this whole function, because of this exponential minus t dependence that you see here, is a transient part, because it changes with respect to time. So there is a steady state part and a transient part. Now, if you do this, so this is the input to the system, applied voltage, which is ramping up with respect to time. Then you start to see, you plot this current as a function of time. Okay, current as a function of time. This part, the steady state part, is going to be independent. So, but then the initial part will be always dominated by the exponential decaying function. So it will decay, there will be a exponential decaying function. The magnitude of this exponential decay is again going to be determined by T by RS CD, nothing but T by RS CD. That is why this becomes very important. The output to the system in terms of resultant I is going to be exponentially decaying function, which is going to be which is going to be dependent on T by RS. And then, but then this current exponential decay is not going to reach to zero. In the case of potential step that we saw here, this current at infinite time t reaches to zero. I tends to zero as t tends to infinity. But here we can't do that, because you have this new CD, which is a constant component. It gets added everywhere at every time that we consider. You have to add this constant steady state part, that is new CD. And that is why you see that this curve doesn't reach to zero, but at some point, after some point of time, becomes almost parallel to the x-axis. The gap between this is going to be nothing but nu into CD. And this is the steady state current that you would observe in the system. So the essence of this is that if you apply a potential sweep to the system, your current in the system is never going to decay to zero. Rather, it will decay to a steady state value, which is given by the nu and the CD. So this is given by the steady state value is given by the sweep rate of potential, and the maybe not plus, and the double layer capacitance of the circuit. Okay, so then if you say that RSCD is very small, nu is constant, and the instantaneous current is a measure of CD as a function of potential. So for if you precisely know what is the value of nu, because nu is something that you are externally controlling the system. I can say that I will do a 5 millivolt per second is the change in potential with respect to time, which means nu is equal to 5 millivolts. Somebody else can come and say that no, I'll do it at 50 millivolts per second. Doesn't matter. Nu, that you take that nu. So the idea is that nu CD is going to be a constant. Is going to give you the not is going to give you the steady state current. Okay, that's not a constant, sorry. New CD is going, after a particular time, the current is going to be equal to the new CD, from which you can calculate the value of capacitance, the double layer capacitance, provided you know the nu, which is controlled by you, and you measure the current, which is again a part of the circuit. You can measure the current, you know the value of the sweep rate, and therefore you can calculate the double layer capacitance. And all these is valid for a small potential step, or for as long as the potential is small, because the overarching condition that we have imposed on all these three is that everything is an ideally polarized interface, and in order to keep it as an ideally polarized interface, your potential that you are applying cannot exceed the limit of charge transfer. There, at some potential, if you go higher up in sufficiently higher in potential, or sufficiently change the potential to a large extent, there is going to come a situation where there is going to be either charge transfer from one side to the other, or metal to the electrolyte, or electrolyte to the metal. So you are consciously keeping that out of the picture by making sure that the potential doesn't go anywhere near that. Okay, is this clear? Any questions so far? Hello.
The charge
Yes.
curve look like?
Yes.
What does the charge curve look like? Charge against time.
Charge, you look at it for yourself. I'm not going to tell you that. Please work it out for yourself. I'll give it to you as a part of the assignment. Please work it out. It's going to be something very interesting, I'm telling you. We will look at it. We will look at the physical significance. Right now, I'm not going to tell you that.
Okay, sure.
Okay, so please take it up as a self assignment, and try to see what comes out. Okay, so then we will go now. let us go one step further than this. So far things are clear. Potential sweep, what is the response of the system in terms of current is clear. It is important that we distinguish between potential step and sweep, because potential sweep has a finite steady state part which does not depend on time. Therefore, the system current in the system does not decay to zero. It remains at that steady state value. The minimum it can reach is that steady state value. Now, if we can do one more thing on this potential sweep. If we are applying a plus nu here to ramp up the potential, you can as well apply the minus nu to ramp down the potential to the initial value. The physical sense of it doesn't change at all. The physical picture doesn't change. So you're having a drop in mercury electrode KCl. You are going from say 0 to 100 millivolts at a scan rate of 10 millivolts per second. So that means you are ramping it up for 10 seconds, and then you are now ramping at the same value, the same magnitude, minus 10 millivolts per second. So you are ramping it down by minus 10 millivolts. You are changing it in the negative direction by minus 10 millivolts every second, and therefore within the next 10 seconds you are bringing it back to zero value. So now if you do that, okay, so this is part A and part B of this. So you are ramping it up. Remember, this magnitude of nu doesn't change. The magnitude mod nu is a constant over the entire experiment. It is just the sign of nu. First you ramp it up and then you ramp it down. The sign of nu changes with respect to time. Okay, so the sign of nu changes. Now let us look at the current response. We know that what happens when you ramp it up. You start from a current value and then you decays and falls to the steady state value. This value is the steady state value given by I equal to nu CD. Now immediately you are not given any time for the system to relax. Immediately as soon as you reach some peak value, okay, the VP. So at VP, this is here you are in terms of the output. This is the input that you give to the system. This is the output that you look at, that the system generates. So in terms of the output, you are at this time t, okay, and that say for example a. Okay, and that TA is nothing but here TA. At time TA, you have reached the steady state value, which is given by nu CD. Now, without giving any time for any time for the circuit to relax or for the components to relax, you start decreasing or lowering the ramping the potential down at the same rate nu. Then you start from here. Your starting position is here, but then because there is a minus nu, the magnitude is same but the direction is different. It is minus nu. So what you have to do, you will have to start putting the exponential function again from this point. Only difference is that you are now going into the minus negative current region. Negative current, because now your steady state current is going to be the same equation is holding good, except that wherever you have a nu, you will have to replace it with a minus nu. So this steady state current is going to be equal to minus nu CD. The magnitude is the same. This is the minus nu CD curve. So both, if I call this as say the steady state of A, part the fragment A, and the steady state current of fragment B, the magnitude of steady state current of fragment A is going to be exactly equal to magnitude of steady state current of fragment B. Only the signs are reversed. So you are going from a positive current because you have a positive nu, and you are going to a negative current in B because you have a negative nu. So now I generate the output in terms of time. The current output is in terms of current as a function of time. So now I decide that, okay, I want to do a small trick here. I want to replace this x-axis. Instead of taking it as a time, I will take it as voltage itself. What am I doing to the voltage? This essentially means this hill that you see in terms of the input, I'm going from VI to some value VP, which is the peak potential, and then VP is going back to VI. This is the A part, this is the B part. So I'm going from one potential to another and then coming back on the same track to the initial potential. So if I replace, if I just do a small trick, I'm going to replace my x-axis in this output curve. I'm going to replace the x-axis. Instead of using time, I use potential. I change it to potential. Then what is going to happen? You see that you are going to this is for A, the fragment A. Okay, so I'm going to, there is a transient part and then a steady state part where current is going to be equal to steady state current is going to be equal to plus nu CD, and then from this point I can't put this is because time, I can't go negative time. That doesn't make sense. So I have to keep increasing my time goes only, the time progression is only in one direction. So I put this curve here. But in terms of voltage, I can, what I'm doing is basically starting from this voltage, which is VP, I'm going back to my VI voltage. And so I can go back in, I can go do the current in this direction. In this case, this is the transient curve and this becomes the steady state curve. The magnitude of the steady state curve doesn't again change. It is going to be equal to minus nu CD. Is this clear? Is this clear to everybody? Everybody with me on this? Please let me know.
So can we say that this is good as compared to the last case, because in this case we are not increasing the potential very much and we are coming from the to the
See,
same potential.
there is no, I would, yes, you are right. We are not increasing the potential. We have control over the potential. So definitely this is, I wouldn't say this better or good, or I wouldn't like to compare these three techniques because each of this technique gives us a different understanding of the physical understanding of the picture. Okay, and which is beautiful by itself. If I take the current sweep, I can find out what is the catastrophic failure value, which is also useful to me at some point of time for that interface. Okay, so I wouldn't say this is good or this is bad, or I wouldn't like to put these three techniques, at least 3 or 4 techniques that we have looked in a comparative scale and say that, oh, this is better. The insight which each one gives is unique. Is that okay? Does that
Yeah,
make
okay.
sense?
Yes,
Yeah.
yes.
Yeah. Okay. So now, and definitely there are advantages and disadvantages of both. So in, like you said, in case of potential sweep, as long as you can fix the VI and VP within the ideally polarized limit of that interface, then you are getting a nice little steady state current that you can measure and from which you can estimate the CD. Yes, that is what the second half of your what you said is absolutely true. Just that don't I don't want to bias your thinking in one way or the other by saying that. Okay. So just that I don't want to bias your thinking in one way by saying one technique is better than the other. Okay. So, but to continue, uh, let me just take 2 more minutes. I'll just finish this to continue. So want you to understand, appreciate that we are transposing a current versus time graph to a current versus voltage graph, and in the process you get this kind of a shape where you have a first arm transient part of A, steady state part of A, transient part of B, and then the steady state part of B. So if you were to do it for the second cycle, if you can do it repeatedly, that is, you apply A, B repeatedly, A, B, so on repeatedly, and you look at, say, something like a second cycle. So this is my first cycle where I go from initial to peak back to initial. So, and this becomes my second cycle, initial to peak and peak back to initial, third cycle, and so on and so forth. So this is what we call as you are cycling the potential between two values. You are cycling the potential between VI and VP. You are continuously cycling the potential between VI and VP, ramping it up and ramping down is one cycle. So you are repeating the cycle, and that is why it is called, this technique is called cyclic voltammetry. Cyclic voltammetry. Okay, and then what will happen to the current response in the system? Now we are plotting the current as a function of voltage. So then for the first cycle, yes. So if you were to do it for the first cycle, you will get this curve, this steady state curve. And then the second, the ramping down is going to be this. But for the second cycle, this is going to be the starting point. So then my transient current is going to go in this direction and saturate at the same value, because my nu is not changing, my nu CD will not change, my steady state current is not changing. So for the second cycle, I'm going to, what happened? Right. So this, for the second cycle, what we are doing is we are showing this curve. Please be with me. So for example, maybe I should take a just please be with me for 5 more minutes. Is that okay? I'm sorry. I just wanted to finish this. I don't want to leave this hanging midway. Is this fine? Please. So what we are doing is we are change potential with respect to time is, please believe that all these are plus nu and minus nu. Okay, this is the best I can do. Oh, maybe wait, I should not have drawn this color. Wait, I'll do something interesting. I like to play with colors. So potential, and then this is your first cycle. Okay, much better. Now I will change my ink color and say that this is going to be my second cycle, and then I'm going to change my ink color again to something else, and then say that this is my third cycle. Okay, so then you look at the current response, response of the current in the system. This is the 0, so this is plus I minus I, you can make that out, and I plot it as a function of voltage. So then for the first cycle, what am I going to see? I'm going to see this steady state curve, and then I'm going to end up here because of the minus ramping. Yes, clear? So this steady state, both the magnitudes are same. Now for the what is the second thing? Second curve, I'm going to see this. And then from here again, I'm going to see this. This is the ramping up part of the second cycle. This is the ramping down part of the second cycle. Yes. Now the third cycle, go to the third cycle, which is color green. So the third cycle again is going to follow this. I'm putting everything very close to each other, but basically it is overlapping. Okay, please make sure that it is overlapping. So then what I get is, beyond this the first cycle, if I take the response of the system beyond the first cycle, what I get is always behavior which is going to be like this. So where this represents the transient part, this represents the steady state part. Okay, so and for this experiment of cyclic voltammetry, which I've abbreviated as CV, done on an IPE surface, you get done on an IP interface, you get a cyclic, and this is nothing but current as a function of potential. This is called a cyclic voltamogram. And the nature of the cyclic voltamogram is going to be like this. You can extract both the transient component and the steady state components, and this steady state is going to be exactly mod nu CD, and mod nu CD are going to be exactly equal. Okay.
Subbu,
Yes,
this overlapping curve will be seen only for an completely ideal polarizable electrode,
absolutely,
right?
absolutely, yes. When you have a ideally non-polarized interface, we will look into it, but the basics of this is going to stay. You will see that how a Faradic reaction on top of this is going to get graphically added on top of this. You will see that. And so to answer your question, yes, absolutely. Only for an ideally polarized interface, you will see this kind of a curve. Okay. Is this clear?
Yes.
Is this fine? So now going back to this, and that is what we call as a butterfly shaped curve. It's a, you can, in literature you call it butterfly shaped curve because it looks like a wings of a butterfly, or you can call it in a more precise way as a rectangular curve, rectangular symmetric curve, because there is perfect symmetry. The magnitude of current, the transient, everything is going to be the same across, either you look at the positive side of current or at the negative side of current. Rectangular symmetric curve, which basically is going to be proportional to the capacitance. This area under this curve is going to be proportional to the capacitance, which is capacitance of the interface, the double layer capacitance. We already saw that nu CD, each component is nu CD, so it is going to be proportional to the capacitance of the interface. What is exactly have we done? How many of you know this guy? How many of you know this guy? Array, it's not a very scientific question.
Is that
So
Sheldon?
Sheldon. Sheldon from Big Bang
Yes.
Theory.
Yes, sir. Big Bang Theory.
Yeah, it's a Sheldon from Big Bang Theory. Okay, nevertheless, this guy, what we have done is something very, very unique, because what we have now done by using the interface is that this area now has built up capacitance for it, and that capacitance means that you have stored energy. Stored energy. And what is this energy stored of? This is electrical energy. This is the input signal is the electrical energy that you are giving to the system, and that at the interface forms the electrical double layer, giving rise to capacitance. See the double layer capacitance, which in turn is equivalent of storing electrical energy in the form of double layer. So now what we have done is basically take this interface and used it to store electrical energy. It is now doing the same job of a battery, but without any chemical reaction. There is absolutely no chemical reaction happening. Because why is that no chemical reaction is happening? Because nothing is transferring across the interface. Only the electric fields are playing across the interface, playing around at the interface. There is no chemical change in the system. If you take sodium chloride or potassium chloride, it will continue to be sodium chloride or potassium chloride. Mercury will continue to be mercury. No, absolutely no chemical change in the system. But nevertheless, because we have created this double layer, the dynamics of the double layer, the kinetics of the creation of the double layer means that we have stored energy into the system. So this is a device that we are now starting to move away from the conventional or what we have discussed so far as just being an interface. It is no longer just an interface. It is an interface which can store electrical energy for us. It takes in the external energy in the form of electrical energy and stores it in the form of electrical double layer. Okay, whether it stores a meaningful amount of energy, whether it can store as much energy as a battery can, no, that is all different question. But the conceptually, it can store energy for us, electrical energy in the form of double layer for us at the interface. Okay, is this clear? This is a very important conclusion, extremely important conclusion. Okay, is this clear to all? Does this make sense? All this makes sense? Please speak up. So
Yes.
yeah, that is the case,
Yes.
then we will stop here. Okay, we will look at what to do with this energy. We have stored some energy, so we will now look at what we can do with that energy. Like somebody pointed out, this is the capacitance is of the order of microfarads. So the energy that you're going to store is also going to be proportionately small. It is not a large amount of energy that you're going to store. So, but there are very interesting possibilities that arise because of that energy stored across the interface. Very interesting possibilities. We will see it in the next 3 classes, the next week. Okay. Is this clear? Any doubts? Any questions so far?
Subbu,
Yes.
I just want to confirm one thing about the assignment.
Ah.
Like generally we take the unit of CD as a microfarad per meter centimeter square.
Ah.
But in order to prove that
No.
RC,
The capacitance is only capacitance. Just take
yeah,
the unit of capacitance. Not.
yes, yeah.
It is not specific capacitance.
Yes,
It
yes.
is not normalized to area.
Okay.
Okay. The new CD there is just CD is the double layer capacitance.
Yes, yes.
Okay. You divide it by the area, that becomes specific capacitance or normalized capacitance. That's not the unit that has to be used.
Okay.
Okay. Yeah. Then you would never end up with the unit of time. You will get time
Yeah,
per unit area, which is
yeah,
very,
yeah.
I don't know what that will be. Time per unit area. That's an interesting. So that actually can have relevance in space-time curvatures. Because if you look at you have seen this the space-time what is this called envelope, the space-time envelope which gives rise to gravity. Right?
Yes, sir. Was sheet
Nobody.
like
Yeah, it's a sheet which it's a trampoline where you put a heavy ball in the center. That is how I
yes,
imagine it to be.
yes, sir. Yes.
So the space-time curvature is what gives rise to gravity. So that is probably where you will get time per unit area. Okay, so yeah, so to answer your question, no, say, just take only capacitance unit, farad. Okay, don't get me wrong. I'm just trying to think aloud, and I'm not. The question is very valid. I'm just trying to see what it can lead to. Time per unit area. I can only think of space-time curvature. I don't know what other physical thing I can think. We can. Yeah. So Sabiha Parveen. So don't get me
Yeah.
wrong. Huh? I'm
No,
not.
no, it's fine.
Yeah. Anything else? Okay. Yeah. Then no other questions. Oh, let me stop recording.